Hello.
Hello.
Right. I'm just waiting for everyone to join. Hello. Hello, David.
Hello.
Hello.
I've dug out some lovely questions.
All right.
So there's a PDF of questions I've just emailed you. I don't know if it's easy for you to distribute them to the students.
Oh, will do. Certainly. So are we going to talk about A-level questions today?
Right. So you gave me a choice, which was to either talk about sort of A-level questions or to talk about the Gaussian.
Yeah, because I think initially we were talking about some A-level questions.
Yeah. So what I found is it's not from an A-level paper, but it's like A-level kind of standard. But it involves it's adapted from a step question. But it involves the Gaussian. So I thought I would I thought I would multitask. And for those in the know, it will give a proof of a special case of the central limit theorem, which will be very, very nice. And it will be a technique that the physicists will absolutely certainly meet again.
All right, perfect. Okay, so questions for today's webinar. All right, so I need to make you host. Right, so to participants. Oh, here it is. Make host.
Excellent.
All right. Yeah, so just a few words. So this is the final webinar for year 13 this year.
Oh my word.
Yes, so the year 13s are off doing exams. So we are sending them off. So well done for completing COMPOS year 13, and some of you, I believe, completed both years, year 12 and year 13. So well done to everyone. We hope that this is not the end of COMPOS for you, because we do hope that in a year's time, so a year from now, you will consider joining us as tutors.
Yeah, that's a good idea.
Because this is what we want to create. We want to create a system where students come in, we train them. Well, right now for 2 years, but we're going to start in year 10. So we train them for 4 years. They go off to university, and when they reach second year of university, they become our tutors. Okay, so we pay money for our tutors. This is a great job opportunity. This is a great line in your CV, etc. Being a tutor at Oxford University. It's always nice to have that. And of course, when you start teaching, you start understanding maths and physics on a whole different level. This is definitely true for me. I completely reviewed and just reassessed everything I know, and it just falls very nicely. So if you're keen to join us, I'll be happy to. In a year's time, just send us a note. I would like to be a tutor, and yeah, hopefully we'll start off. So good luck with the university, all of you. Good luck with your exams, and off to you, David.
Okay, I've got an absolute treat. Just to let you know as well that I've got another meeting at 7. So this is going to be a slightly shorter webinar. But Dr. Chernov sent you a compilation of questions, A-level standard.
It's on Slack.
And
yeah.
I'm going to do question E9 for reasons I just explained when people were present at the start, that I was sort of given the choice to either do a Gaussian question or a sort of A-level standard question. And I thought, how about this? This is a sort of step kind of level question, but it's got the Gaussian integral, and it will prove a very special case of the central limit theorem for free. I think it kind of has got nice gears, and Dr. Chernov will be able to tell me what he would call the technique in part C, and might as a physicist, I know what I would call it as a mathematician. But anyway, let's get going. So let's look at part A. So it says find an exact simplified expression for the integral 0 to infinity of x to the n e to the negative x. So suggestions in the chat of what method of integration do you think you would use to integrate x to the n times e to the negative x? So the first thing to notice is that we've got a product of two functions. The e to the negative x is nice and easy to integrate, and the x to the n will differentiate to something simpler. And so I'm not surprised to see in the chat suggestions to integrate by parts. So I'll put u equals x to the n, u dash is nx to the n minus 1, v dash is e to the negative x, and therefore e is negative e to the negative x. And so I've got when I integrate by parts, I get two negatives, so I get plus n integral from 0 to infinity of x to the n minus 1 e to the minus x dx. So I've just used the integration by parts formula. When I substitute in my upper limit, I think you should agree with me that the exponential decays faster than the x to the n grows. If you don't believe me, then remember, if x is bigger than 0, e to the x can be written as an infinite expansion. And so in particular, it's got a term in x to the power of n minus 1, which will grow faster than the x to the n term. So I can say that e to the x is bigger than x to the n plus 1 over n plus 1 factorial. So e to the negative x times x to the n is less than n plus 1 factorial over x. And as x gets big, this goes to 0. Okay, so here I've just very carefully shown that when I substitute in the upper limit, this exponential goes to 0. When I substitute in the 0, 0 to the power n is 0. So both the upper and the lower limit here is 0. So I get I to the in is the integral from 0 to infinity x to the n minus 1 e to the minus x dx. What do you notice about this integral? So this integral is almost identical to my previous integral, except that the power has come down. So I could write it, indeed, I could write it as in minus 1. But what I can do next is I can play the same game. So what can I say that in minus 1 is equal to? Well, all that's changed is the parameter. So it's n minus 1 times in minus 2. And then I can keep playing the same game all the way down to I1, which is 1 times I0. And now if I substitute everything back in, every time I go down a step, I multiply the next number down. So I can say that in is n times n minus 1 times n minus 2 times 1 times I0. But I0 is just the nice integral from 0 to infinity of e to the negative x dx, which I can just integrate by recognition. And if I substitute in the upper limit, I get 0. If I substitute in the lower limit, I get negative 1. So overall, I get a 1. So I to the n is equal to n times n minus 1 times 1. But is there a simpler way of writing this? Well, we recognize this as n factorial. Okay, so we have this nice result that the integral from 0 to infinity of x to the n times e to the minus x dx is n factorial. Can anybody give me a reason why this result is cool? Why can you do, there's something that, it's a little bit of a flight of imagination. I think it goes back to Gauss. But there's something that you can do at this point, which is really quite exciting. So n factorial makes sense for what type of number? Okay. N factorial only makes sense for whole numbers, counting numbers. But the integral on the left, and I'm not saying it's easy, but the integral on the left makes sense even if n is not a whole number. So for example, this integral, I don't think it'd be a particularly easy integral to do. You can try, and if you try it, you'll see why I think it goes back to Gauss. But can anyone tell me what would be a sort of natural thing to call this integral? Well, this is the integral from x to the power of a half e to the minus x. So it would be natural to refer to this as you could now say, we could just define this as a half factorial. So what, and this is a process called analytic continuation, and it's something which is done in maths. But you could define a function, and the function is called pi, which is the integral from 0 to infinity of x to the alpha e to the minus x dx. And on the natural numbers, this is equal to n factorial. For non-natural numbers, this is just what you define n factorial, the factorial to be. So you could define this as alpha factorial. I can't remember the exact figure off my head, but a half factorial is something like the square root of pi. Okay. But that's part A was repeated integration by parts. Okay. Any questions about part A, or are you happy for me to continue, in which case put a thumbs up? Good. Right, let's look at this. So it says the functions fn are defined as the natural log of x to the n e to the minus x. And it says find the position x0, y0 of the turning point of fn and classify its nature using the second derivative test. Okay, so first of all, x to the n e to the minus x, it's clearly 0 when x is 0. When x is 0, it clearly tends to 0 as x goes to infinity. So it presumably looks something a bit like this. And what we're trying to do is find the position of this turning point. So it's late on a Thursday evening, but we should be able to differentiate and find turning points if my stylus works. So fn-x, it's just a chain rule. So I differentiate the bracket using the product rule. Now divide by xn e to the minus x. And I can divide everything by x to the n minus 1. So I get n e to the minus x minus x e to the minus x over x e to the minus x. And the e to the minus x's go away. So I just get n minus x over x. So where is the turning point? So fn-x equals 0 if the numerator is 0, and that happens if x is equal to n. And then it says, show that it's, use the second derivative test. Well, I can write this in a slightly simpler way as n over x minus 1. So the second derivative is nice and straightforward. And so the second derivative is negative, which means that there is a maximum. Okay. So for example, at x equals n, the second derivative is negative 1 over n. Okay, so this is the function y equals log xn e to the minus x. Sorry, the sketch there was just xn e to the minus x. The logarithm of that I don't know too much about it, but it's got a maximum at n ln xn. Sorry, n to the n e to the minus n. Okay, so the answer to part B is that it's got a maximum at x equals n. Okay. How are we doing with part B? So if you are happy with that calculation or happy with the ideas behind it, then put a thumbs up into the chat. If you've got any questions, let me know. Oh, so it says, why can you interchange log for learn? Once you get into a certain level of mathematics, if you see a logarithm, then it's likely to be the natural logarithm. So in the context of this question, I just wrote log to mean learn. You'll go to university saying learn and you'll come out saying log. Okay, let's look at what the question invites us to do next. So what it invites us to do is it invites us to find the Taylor series of the Taylor approximation of that function close to the maximum. Okay, so let's have a go. So we've got fnx. So they've even given me the Taylor expansion. This is approximately equal to fn at x0, which we know is n, plus fn dash, so the derivative at x0, and then plus a half times the second derivative at n, and then we've got this quadratic term. Okay, so let's do the various parts. The function evaluated at at n, we just need to substitute n into the function. So we get ln n to the n e to the negative n. What's the value of fn dash n? Let's see how awake people are. I could scroll back to where I'd differentiated, but remember that n was the point that we picked n to be the maximum. So the derivative at n is just 0, and we calculated the second derivative at n as negative 1 over n. So we've got negative 1 over 2n x minus n squared. So what that means is we've got this complicated function, but close to the maximum, we've just approximated it as a parabola. Okay. I don't know if Vlad is still on the call. I'll give him time to unmute himself, but he might want to jump in and explain the physics better than me. This is something which physicists do often, because if you're in a sort of potential well, the one potential that people understand is the potential of the harmonic oscillator. And so if you approximate the potential by this quadratic term, close to the origin, it's going to do simple harmonic motion. Okay, so right, so we've got the approximation to our function. We now remember what our function was. It was the natural log of x to the n e to the negative x. And now I can just exponentiate both sides. So I get x to the n e to the negative x is approximately n to the n e to the negative n times the exponential of the other part. And now I'm going to do something a little bit funny, and it's not asked for in the question. I'm going to divide by n factorial. Okay, and so we've got x to the n e to the minus x over n factorial is approximately oh no, I don't really want to do no. Sorry. I want to divide by, no, e to the minus x. Yeah, I'm going to divide by n factorial. Right, I want you to stare at this, and I'm going to ask one of my favorite questions, which is, why is this interesting? Good, the integral is 1. That's a good observation. So we know that if we integrate the left-hand side, we're going to get 1. Where else in your mathematical studies have you seen where have you seen something that looks like x to the n e to the minus x over n factorial? Okay. Okay. I could do it slightly differently, I suppose. I could write it as lambda to the n e to the minus lambda over my stylus is, I think my stylus is out of battery. Over n factorial. Excellent. It's a, oh my word, between the two of you, Aska and Noah, I'll just put this has made me so happy. because this is the point of this question. Yeah. So what we've got is a Gaussian on the right, and we've got a Poisson distribution on the left. Okay, so what this question is really about, even though it's just using A-level maths, is the central limit theorem. Okay, I think it'd be worthwhile just illustrating this for a second, just to show you what I mean. Too many windows open. I'm just going to share my screen. Oh, where's Mathematica gone? So what I'm hoping to illustrate is this. I want to illustrate graphically this observation that Asker and Noah have made, that on the left we've got a Poisson, the mass function of a Poisson distribution, and on the right we've got a Gaussian. So let's just see what this means. So syntax. Okay, so what I'm generating here is like the first my computer's being so slow. So here we go. Okay. So what we can see is that I've plotted the probability of a Poisson distribution being equal to a certain number with lambda equals 5, and we go up to a point and back down. And what I'm going to do is I'm just going to manipulate my value of lambda . And so as that value of lambda becomes big, we get something that looks very familiar as our familiar bell curve. Okay, and it should be noted that a Poisson distribution of with parameter n has got if x is Poisson n, then the expectation of x is n. So that's why this Gaussian has got a maximum at n, and the variance of x is also equal to n, and that's just alerted me to something that I've lost this n here. So this n here is because the mean is n, and this n here is because the variance is n. And then this constant out the front must be the thing what is tied down about a Poisson distribution is that the masses sum to 1. What's tied down to the normal distribution is the total integral should equal 1. So this constant should determine should ensure that the integral is 1. Okay, so before we go on, is everybody happy with not particularly difficult calculation to get this approximation? If so, put a thumbs up in the chat. If not, put any questions in there, and then I'll just get the next part of the question. I hope you're enjoying this question. Every question on this sheet is designed in a similar way, that it's not necessarily that the maths is super hard, but the maths has been designed, it was written by me and a colleague at Sevenoaks School, as you'll see at the top, when we were teaching there. But the maths has been designed to actually illustrate kind of mathematical principles. So let's look at the final part of the question. So it then says, integrating the approximation 6, so this approximation here, and making use of the famous result that the integral from -infinity to infinity of e to the -x²/2 is √2 pi, establish this approximation. So let's do that. So if we just integrate both sides of the approximation, and assuming, and this is the sort of thing when you go to university you'll just be much sharper about, assuming that the integral of two things which are approximately equal, then we integrate from 0 to infinity of n to the n e to the -n e to the x minus n squared over 2n x. So on the left, does anybody remember what this integral on the left was equal to? Well, that was the integral that we did in part A, and that was the integral that we found was n factorial. On the right, we want to be able to use the sort of standard Gaussian. So I want x minus n squared over n to be u squared. So in other words, I want x minus n over √n to equal u. Okay, so let's use this substitution. So dx by du, I've got x minus n is equal to √n u. So it's just √n. So dx is √n du. Notice that these terms look complicated, look like they're going to make the integral hard, but they just involve n, they don't involve x. So we can just treat those as a constant. When x is 0, the lower limit is, sorry, u is 0 subtract n over root n, so that's negative root n. And then the upper limit is infinity. And then we picked it so that x minus n squared over n, so this term here is u squared. So this is e to the minus u squared over 2 du. But we want to use the famous Gaussian result, which goes to negative infinity. But as n is large, as n becomes large, negative root n becomes negative and becomes negative infinity. So we can say that this is approximately, oh, and sorry, I need an extra root n as well from the integration by substitution. So now I'm almost done. So I've got n, the root n makes n to the power of n plus a half. I've got my e to the minus n, and then I've got my standard Gaussian integral. Got this thing, which is root 2 pi. So it says integrating the approximation 6 and making use of this famous result, establish for large n that n factorial is approximately root 2 pi n to the n plus a half e to the minus n. And this is a famous result, and this result is called Stirling's approximation. Okay. Does anyone have any questions about that last? Does anyone have any questions about that last part? The main observation is that we know that this thing integrates to 1, so the right-hand side must also integrate to 1, essentially because we're making probability distributions. So yeah, Aska, this is Stirling's approximation, and this square root of 2 pi is the best possible constant within Stirling's approximation. Okay. If everybody's happy that this question is done, do you want to put a thumbs up in the chat? Okay, so I hope you agree that this was a very nice question. So the big idea in the first part is one of analytic continuation. So what we can do now is attribute meaning to factorial numbers which are not whole numbers. We've then got this nice idea of taking a complicated function and approximating it by a parabola close to the maximum or minimum. And that's something which you'll meet again a lot in physics, where you can approximate sort of oscillations close to the minimum of a potential well as being similar to a harmonic oscillator. Here we've got a nice little bit of maths that links the Poisson distribution to the Gaussian distribution. So Gaussian on the right, Poisson on the left. And then if we integrate, it allowed us to get the constant in Stirling's approximation. So I don't know. That was my pitch for that being a nice question. Right. We have got about 10 minutes before I need to go to my next appointment. So as I said, we needed to finish a little bit early. So you've got 10 more minutes of COMPOS webinars. Does anyone have any requests of things they would like me to do in the last 10 minutes? So that could be other questions on the sheet that Vladimir's sent round, could be questions on the Gaussian sheet, could be questions about life at university, anything. I'm open to your requests. How do you properly sign up to be a tutor? I'm not sure. That you'll need to check in with Vlad about that. Okay, well, any other requests? No. Okay, I don't know if there's going to be. I mean, I love Stirling's approximation. I think Stirling's approximation is sort of like a highlight of like elementary mathematics. So mathematics before it gets sort of particularly complicated, stuff you can just do with, you know, as we saw with A-level maths. This is a particularly beautiful argument of how the mathematician Euler got this constant square root of 2 pi. And actually, I think in the interest of time, I'm not gonna get this done in 10 minutes. So I'm just going to put this into the chat as as a little bit of. Could you talk about the Dirac delta part of assignment 9? Yes. Okay. Yes, I can. Oh, there's this webinar from last week, which was horrible, where my stylus wasn't working. So I think the best way of thinking of the Dirac delta function is as a probabilist. So I think the best way of thinking of it is as being the density function of a point mass. Okay, so for example, you know that if you've got a continuous random variable, that the expectation of x is the integral from minus infinity to infinity of x fx dx. Okay, but let's imagine that we've just got a really, really simple random variable where the probability that x is equal to a is equal to 1, and the probability that x does not equal a is equal to 0. Okay, so this isn't a random variable. Yeah, another name for this random variable is just a. Okay, so it's non-random. But what would be the expectation of a? Well, it would clearly just be a. Okay, what would be the expectation of x squared? Well, it would clearly just be a squared. So what does the density function do? The density function just picks out the value of whatever function you had before it. So the expectation of g of x is just g of a. But the density function of this point mass is just a Dirac delta function with the spike at a. So it's just delta x minus a dx, and that's equal to GA. Okay, and then this gives me, so this is almost a definition of what the delta function does. Okay, so it's just, when you integrate against the delta function, you just evaluate the other function at that point. Okay, and the way you can make that precise is that if you had a real density function that was just a real spike, well, which was a very, very sharp spike, broadly speaking, it would just ignore everything that the function does except very close to a. Okay, so that's what the delta function does. The delta function you can also integrate. Okay, so this is my delta function. It's just a big spike at 0. Now, if I integrate from negative infinity to a of a delta function, if a is negative, I haven't reached the spike. So I've just integrated where the function is 0, so it's 0. If a is positive, then I've gone past the spike, and so it becomes 1. So my integral of my delta function up to a is this function, which is 0 for negative numbers, and then 1 for positive numbers. And this is called the Heaviside function. Actually, I'll tell you a really advanced fact about the Heaviside function that I only realized long into my PhD, and it absolutely blew my mind. So I always thought that the Heaviside function was called the Heaviside function because it was heavy on one side. So it's like 1 on this side and 0 on this side. So it's sort of light on one side, heavy on the other side. And I remember it just absolutely blew my mind when I discovered that there was a mathematician called Heaviside, and it is named after Heaviside. Notice that if you differentiate a function, you get its gradient. Now, what is the gradient of the Heaviside function? Well, here it's flat, so the gradient is just 0. Here it's flat, so the gradient is just 0. But at 0, there's temporarily this infinite gradient. And that just corresponds exactly with the Dirac delta function as being something which spikes at 0. Okay. Does that answer your questions about the Dirac delta function, or is there more that you would like to ask? Yeah, this turns out to be a very important fact, that the Gaussian function, the Fourier transform, is a Gaussian function. As a very, very brief aside, we had a maths and physics speaker in my school last night, and she works in magnetic resonance imaging. She does brain imaging, looking for sort of like early diagnosis of Alzheimer's. And she said that the sort of main maths that she uses is Fourier transforms. And as after dinner, I was just saying Fourier transforms, I think, is like the bit of maths that ends up being everywhere. But the first time you see it, it's really difficult to think, what was Fourier doing? Why did Fourier think of Fourier transforms? So if you're not quite sure what they do, why they do it, why they're important, you're not alone, but you will see them again. You'll see them in quantum mechanics, you'll see them in probability theory, which is my world, and then you'll see them in lots and lots of applied mathematics as well. Okay, I will need to go. So yeah, I hope you've enjoyed the COMPOS webinars. I hope you've, I don't know quite how many I've done for you over the years, but I hope you've enjoyed my sessions. I hope you've learned interesting maths. And yeah, good luck in all your future mathematical journeys. Okay, bye-bye everybody, and have a lovely evening. Oh, thank you. And God, it's funny, it's so strange because, like, yeah, you're year 13, so side thing, good luck with your A levels. But most importantly, I hope you really enjoyed the COMPOS sheets, which are much more interesting and exciting than A level. So thank you very much, and good night.